so you can actually fulfill the course requirements. So if you're auditing the class, just send us an email with your EID, and we'll get you put into Canvas, and then you can fulfill the writing requirements. So please do that. Second comment, next week is Energy Week here at UT. Very busy week, so we will not have a Energy Symposium speaker next week. There's so many other things going on. We figured we'd rather have you attend some of those than worry about coming to this meeting at 5:15 next Thursday. So next Thursday, or actually next week, go to Energy Week. It is free for students. Get in there. Dave's going to shoot me when I say this, but there's food. And we usually have too much food. So please come on over to Energy. Yeah, you're grimacing now.
What happened this week?
We always have too much food. We always seem to overbuy. But come on by, there might be food. But please, attend as many of the sessions as you can. I know you're going to class and all, but if you have an opening, look at the schedule, see what's going on, come on over. Please try to attend those. What was the third one? So since we don't have a talk next week, the following week will be Eric Benedict from the Stockholm Institute. He's going to be in town talking to us about energy technology, the development of energy technology, and how it's affecting the lay of the land out there, so to speak, and how it's influencing things. So that'll be 2 weeks from today. Please come to that one. Not just because it's going to be a great talk, but it's embarrassing for us when we pay money to bring people in from out of town, and they come in here and there's just crickets in the room. It's nice to really pack the house for our speakers who come in from out of area, as well as those from the local area, but those are easy. Okay? I think they covered all the administrative. Was that it, Harsh?
Yeah. I thought you were going to miss the third one, the Oops moment. Department of Energy.
Oh, yeah.
But you remember. See, you remember.
So finally, today we have, if you didn't realize it, it's homecoming week. We have Dr. Daniel Zavala, who is a UT grad. He did both his master's and his PhD work here. Very successful student, and he is now in his third year at the Environmental Defense Fund. Some of you may know him, some of you may have done some work with him, or some of his peers there at EDF. His focus the last several years has been on methane emissions, and in particular super emitter sources. So I'm not going to lead too much into what he's going to talk about tonight, but I think you'll find his talk very compelling. And one final admin note, we will be going out afterwards to continue the discussion. I will be hosting, and it will be at Varsity, is that what they call it? Yeah. At Varsity. So if you want to join us over there on the other side of campus, have an adult beverage, maybe a little pizza, and continue the discussion, please come and join us. We'll probably get over there by around 6:30, 6:45. Any questions before we get started? Great. Well then, Daniel, welcome, and it's all yours.
Thank you. Thanks for the invitation. It's always nice to come back to campus. So I started working with methane emissions from the oil and gas system as a grad student, and then now at the Environmental Defense Fund. We started looking at the emissions in the US and then transitioned to the international oil and gas system. So we were driving in the summer, the highways in Netherlands looking for gas production sites. And then in the middle of one of the highways, we see this sculpture. I thought I had seen methane for many years, and I was starting to see methane everywhere. So we took pictures, drove around, and then it turns out after some research that the gas company that produces gas in Netherlands, NAM, created this sculpture as a 50-year anniversary for their first drilled well. So it's a nice metaphor to what we've been doing and what I've been doing for the last several years. I'll divide this presentation in 3 parts. The first is why we should care about methane and its climate implications. The second part, what have we learned from research in the US through the last 5 years? And finally, what does this all mean for the global oil and gas system, and what have we started to learn as we look at other places outside of the US? So a lot of you most already know this. Methane is also a greenhouse gas. In the short term, the first 20 years after being emitted, 84 times more potent than carbon dioxide. So if we want to look at climate benefits in the short term, reducing methane presents as a great opportunity. And because the impacts of climate change are already being experienced in present times, and it's not a future problem, we should care about methane and other short-lived climate pollutants. Actually, methane would be responsible for roughly a quarter of the global warming we experience today. There have been several papers looking at mitigation strategies and temperature change, of doing either just carbon dioxide mitigation, just short-lived climate forces mitigation as methane, or doing both. And the only way of really slowing down the current global warming rate is to focus on both. So EDF's perspective on focusing on methane emissions is not just to say, let's do this instead of carbon dioxide, but by coupling both ideas, we have the best chance of success. So we call this the AND proposition. There are several short-lived climate pollutants focusing on methane. If we think of anthropogenic sources globally, the main sources would be livestock, like enteric fermentation and manure management, rice production, leaks from the oil and gas system, including pipelines and the entire supply chain, and waste. I'll explain a little bit why the specific focus on oil and gas, and that's going to be the majority of my talk. But it's also important to say that EDF is working on livestock emissions, so we're trying to figure out if manure management is an issue for methane emissions globally, what can be done to reduce those emissions. In a similar way, in Asia, probably the major driver of methane emissions is rice paddies. So we're working with farmers in Asia in what's called climate-smart farming to find ways to increase the yield of rice production while minimizing the emissions. The reason for focusing on oil and gas, and I hope that's a message that comes clear through my presentation, is that we actually know how to reduce the emissions. So it's not just that it's a big issue, we know the solutions and they're cost effective. This also gives me a chance to briefly mention kind of two guiding principles of the place where I work, the Environmental Defense Fund. We work on a wide array of environmental topics, but we always, one, decide to work on the ones that we can propose a solution, and two, we base those solutions and advocacy on science. The other just brief interesting aspect when we think of the oil and gas system is that the different environmental implications, so here we have methane and climate change, we can have air pollution for some particular parts of the processes, water pollution. It's always this sort of interplay between the scales at which the problems happen and this local, regional, global interchange of scales sometimes make it hard from a political perspective to find solutions and to get the different stakeholders to agree on what's the right path forward. If we go from the global sources of methane to what's happening in the US, the oil and gas system is responsible for a third, according to the 2014 version of the EPA inventory. So oil and gas system is a major source. Other important sources already mentioned, enteric fermentation, landfills, coal mining, manure management, and wastewater. Another topic that has recently got a lot of attention from the scientific community is the rise in methane concentrations in the atmosphere. You might have seen a similar plot for carbon dioxide, but this shows from 1980s to 2010 average concentrations of methane in the atmosphere. What got the attention of the scientific community was that for the first part of the year 2000s, there was kind of a flattening in the increased trend. And then at some point around 2007, there's an increase in the trend. So there's been a lot of research trying to explain, first of all, why we saw that flattening, and then what could have caused the increase. Another way to look at that same increase is when we see the annual growth rate, and we can clearly see how around 2007 it starts growing again. More than probably a dozen papers have appeared just in the last year coming with hypotheses of what's driving this change. All of them are peer-reviewed, so it's clear that there's no one single answer of what's the driver for this growth rate. The three main explanations, the first one being relevant to this talk, is that there's been an increase in fossil methane, so methane coming from the oil and gas system related to increases in global oil and gas production, and that this is driving the increase in methane concentrations. The second interesting hypothesis is that methane emissions globally, the concentrations have gone up because of an increase in biogenic methane that could be caused by a combination of agriculture and wetlands. The third explanation is that actually methane concentration hasn't gone up, but what has gone up is the concentration of the main sink of methane in the atmosphere, the hydroxyl radical. There are still unclear explanations of what could have happened or caused the increase in the hydroxyl radicals in the atmosphere. However, at least it seems in the same level of a parsimonious answer as the other two. What we do know, early on in this debate, there was the idea that perhaps the increase of methane concentration was driven by methane releases in the Arctic. We know that's not the case, and that the increase in emissions, or the cause for the increase in concentrations, is happening outside of the Arctic. We can probably expect that it's some combination of these three major drivers.
Can we add livestock production to the second?
Yeah, livestock production. Yeah, so livestock production would be sort of in the agriculture aspect of it. So for the second one, livestock production, as well as, for example, rice production in Asia would be one of the explanations thrown. We would say all of them have a role to play in those changes in the concentration, but if we already know how to reduce and minimize emissions from the oil and gas system, it's clearly one of the paths that we need to move forward because of methane implications with climate. So now, zooming into the oil and gas system, one of the first debates about the role of natural gas was the idea of proposing natural gas as a substitute for other fuels, for example, coal, based on the idea of a lower carbon footprint. If we just looked at the carbon dioxide emissions as a result of combustion by itself, so we just did a snapshot on combustion, it would be true that natural gas is this cleaner fuel. However, we need to look at the methane emissions that are happening all the way before combustion to get the whole story. To analyze this a little bit further, a few years ago, we proposed a term called technology warming potential. The idea is to add up emissions from the life cycle of methane and carbon dioxide of two technologies that we want to compare to analyze the climate implications. In this example, I'm doing diesel against natural gas. So the question we would try to answer is, does it make sense in terms of climate benefits to convert trucks that use diesel to natural gas? What this plot is going to show, so this is the years after the conversion of the technology. If the technology warming potential is above 1, it means that the technology switch we perform is damaging the climate. And if it's below 1, we see benefits. So when we plot this for the change of diesel to natural gas, we see that it would take roughly somewhere like 100 years to get to the point where we see climate benefits. So this type of analysis allows us to see if specific changes and specific usages of natural gas make sense or not. Another way to show that information is just to estimate from that same technology warming potential what would be the rate of methane from the natural gas supply chain that would have to go to the atmosphere for that climate benefit to disappear. So if in any of these lines we're above the line, it would mean that we're not achieving benefits. So one of the most known cases is when we talk for electricity production, changing coal power plants to natural gas. In the short term, let's say 20 years, if during the production, gathering, processing, all the way until the gas gets to the power plant, what's being vented into the atmosphere is more than 2.7%, the technology switch makes no sense. As we move forward in time, we have a little bit more flexibility. An interesting case is for heavy-duty vehicles where there's a lot of uncertainty on the total emissions that are going into diesel trucks, for example, or natural gas trucks. However, it's interesting that the line 1 is pretty flat and the percent is very low. So, in other words, there's very little margin of error for the total methane emissions that would make this technology switch not providing climate benefits. And it's true that the analysis needs to be wider because changing from diesel to natural gas might have other benefits, for example, in terms of public health or air quality, but just in terms of the climate perspective, if emissions would be above 1%, it would make no sense to do this technology switch. So when this analysis was first presented, we knew that for the first 20 years, if emissions from the natural gas supply chain in the US were above 3%, changing from coal to natural gas made no sense. But there was a lot of uncertainty on, well, what is the actual leakage rate and where are the emissions coming from? So EDF launched a set of studies characterizing emissions from the entire supply chain, so production, gathering and processing, transmission and storage, distribution, and end use. The idea was to perform measurements to get an emission rate and to be able to analyze how to reduce the emissions. Another kind of brief summary of the way EDF as a non-profit environmental organization, not an academic institution, was conducting the science. The idea was to catalyze science. So we partner with more than 30 academic institutions so far. All of the projects were led by academic scientists. The idea was that for each stage of the supply chain, we would use more than one technology to provide head-to-head validation. There was an independent committee of scientific experts checking each of the studies. All the data produced through these studies is public, and it always finished in a peer-reviewed journal. The US part of this project is almost on its last stages. We're working in the synthesis of what this all means. This is part of what I'm going to show right now. But so far we produce almost 30 peer-reviewed publications, and the list of academic and industry experts that have been involved in the project, it's over 100. So getting a little bit into the methodologies, there are two main ways in which we can classify the methods used to measure methane from the oil and gas system. The first one, referred to as top-down methods, is when you use something like an aircraft that is flying around, let's say, a production region. So this is good because with one fly, you get the total methane estimate. However, there might be other sources within the region. For example, you can have, like in Texas, you can have a lot of gas or oil production sites, and in the same places you have livestock. So you get the total number, but it's hard to know what is a contribution from the source you're interested in this case, oil and gas. The other way, or the complementary way of doing this, is what's called bottom-up methods, and is the way the inventories are usually built. So you would select a limited number of facilities. You would go into the facility and make measurements on site. The limitations of this is that, you would try to get as big of a sample as possible. However, you're going to always get into questions about how representative this is and how to scale from a limited number of samples to a number that is representative of the entire population. The reason I show these comparisons between methods is because when different research groups started looking at methane emissions from the oil and gas system in different parts of the US, the studies that used top-down methods always throw numbers higher than the bottom-up. So this is a chart showing every row is a different study, and I'm getting the ratio of top-down versus bottom-up. There are different types of bottom-up or inventories. GHGI, the square, is the EPA greenhouse gas inventory. GHGRP is our reporting program, very specific reporting program. I'll get into that, from the EPA. And EDGAR is a global inventory of emissions. But so what we see is that all of them fall above 1, even almost 1.5 ratio, meaning that the top-down was always significantly higher than the bottom-up. This created a sort of impasse with policymakers, because what they started saying is, there's no clear answer about this issue. We just need to research more without making decisions about how to mitigate emissions. So to answer this specific question, we conducted a measurement campaign in the Barnett Shale in north central Texas. At the same time, we have airplane flying over to get that regional total, and we have teams on the ground getting the bottom-up. So this would be a real top-down, bottom-up comparison, because we would get rid of uncertainties like the fact that if they happen in different regions or if they happen in different times, you might not really know what are the activities that are happening. So this head-to-head coordinated campaign reduced those uncertainties. The main result from this campaign was that for several days of measurements or flights that we were able to take, the results from the top-down and bottom-up were within 10% difference. So in that plot where every other study was above 1.5, this would be below 1.1. So we got agreement, but more important than the agreement was looking into what made the agreement happen. And we found 4 important conclusions that we've been applying to other studies, and we think that they need to be the basis for understanding the global oil and gas system. The first of all is that all the studies that were done previous to this coordinated campaign relied on one single flight. So they were taking the regional number from one flight. There are a lot of oil and gas operating activities that are episodic, and there's also a lot of uncertainty just into the meteorological aspects that go into estimating a regional flux. So if you just have one single estimate to get the total, chances are that you might be off, or you might end up making the measurement in one particular day that one of these episodic, not representative activities was happening. So by having several replicate measurements of the top-down, we were able to constrain that regional flux. As I said, one of the main challenges of the top-down is that you get regional methane, but you know how much of that goes to the oil and gas system. For this particular project, we were able to use ethane, which is co-emitted with oil and gas sources, but not by cows or agriculture, to be able to track what fraction of that came directly from the oil and gas system. There are now other papers that have used, for example, isotope signatures to do a similar role. And then the third conclusion, which is probably the most surprising but easy one, is that when we started tracking the number of facilities that appeared, for example, in inventories, there was a significant underestimation of facilities. For example, our first look at compressor stations in this region from the official reports showed something like 25. And when we started just looking for, using, for example, satellite Google Earth imagery to locate those compressor stations, we found almost 10 times more. So you can have the best emissions measurements in the world, but if the activity data or the counts of equipments are off, you're not going to get the total to agree with the top-down. And finally, and this is something that I'll get in detail in a second that Fred already mentioned, is the existence of super emitters. This is a very small number, a small fraction of the total sites contribute disproportionately to a large fraction of emissions. So this has its own challenges, because if your sample size is not big enough, you're going to miss those high emitters or super emitters. And you also need to think of specific ways in which you derive the emission estimates, because if not, again, they're not going to be representative of the level of emissions that it's actually out there. When we got all these results, got the top-down and bottom-up to agree, and presented sort of this revised inventory, we found it to be 2 times what was reported to the EPA greenhouse gas inventory, more than 3 times what would be reported to this reporting program, and more than 5 times what was reported to this global inventory. It's important to say that after this work was published in 2015, the EPA went and revised their inventory, and now is significantly closer to our estimate. The 5.5 for Edgar has significant implications for the oil and gas system, because this inventory is usually just assumed to be right, or the best knowledge. But if it's 5.5 times low, and it holds to be true for other regions in the world, it's probably not good enough to estimate and track mitigation of emissions around the world. So just a little bit more about super emitters. Across several studies, we see the existence of these fat tails or skewed distributions. This is one example of distribution of emissions, for example, for production sites, percent of sites and percent of emissions. And we could, for example, derive from this plot that 5% of sites accounted for 50% of emissions. So this completely changes the picture of what you need to do to mitigate emissions. It doesn't mean that if you were able to find this 5%, you would be done with 50% of the emissions, because as we've learned, the processes and the causes for those high emissions, we call it sort of like the twinkling star effect, because it's changing from place to place and time to time. An example of that is one of the causes for this could be a malfunction in one of the wells, and perhaps it gets fixed at that particular site, but the same cause could appear at another site. So this disproportionate cause of emissions is moving from place to place in the regions. We've seen it across the country, and we've seen it also across different types of components and different stages of the supply chain. So this is a paper, Allen et al., for pneumatic controllers, which are used to control processes on well sites, 13% of sites, 88% of emissions. If we move to the midstream sector, to gathering stations, 30% of sites, 80% of emissions. The transmission system is similar, 50% of sites, more than 30% of emissions. So this has clear implications for the inventories, because if they don't account for the existence of high emitters, they're going to be off and they're going to be underestimating. And it also has implications for the way you find these sites and you mitigate them. So once we found the importance of super emitters and we saw that the EPA inventory was off, we did a follow-up study trying to understand, okay, is this just some specific component in the inventory that is not being captured right, or is there actually a combination of processes that is not being accounted at all of the inventory because it's this type of abnormal activity like malfunctions. So we created a Monte Carlo model. The orange line is the measurements that we took while we were in the Barnett Shale, and each blue line is one of 10,000 simulations of the emissions we would get out of the EPA inventory. And the short answer here is that this gap would represent those high emitters that are never reached by the emissions contained in the inventory. So by showing this difference, we're able to infer the existence of super emitters and say that they are caused by abnormal processes and not, let's say, routine operation conditions. Another part of this super emitter analysis was to take a helicopter with an infrared camera across different production basins in the US. So we went Eagle Ford, Barnett Shale, Marcellus, North Dakota. With the infrared camera, we would not be able to get a quantity of the emissions, but we would be able to see the prevalence of super emitters and just to try to sort out if there was some operating condition that we could tie that would let us know that a super emitter could happen. So when we started this project, the idea was if we look at 8,000 wells in the US and we know production levels for oil and gas, can we come up with some sort of predictive model to understand where and when a super emitter could happen? This is one example of one of the videos we took. This is in the Uinta Basin in Utah. So this is a wellhead. This is storage tanks. And in a moment, it's going to turn to the infrared. And we're going to see one of the characteristic super emitters that you wouldn't be able to see unless you have an infrared camera. And we saw this happening across all basins and probably driving emissions in all of those basins. Yes, so that's the vent of a storage tank.
Do you know if it's the water or the condensate?
I think that's the condensate. So from this study, when we found super emitters, 90% of them, the emissions were coming out of tanks, mainly the condensate tank. So again, just to summarize the main conclusions from this super emitter work, the large emissions are commonly coming out of tanks. We tried different statistical models to predict emissions, and we couldn't find any significant correlation or regression supporting the idea that this is in a way more unpredictable than, for example, industry was claiming. Super emitters are more common in oil-producing regions than gas-producing regions. Explanation for that could be that if the company or the operator is just going after the oil, it has less of an incentive to take care of the gas. And that's something that is also holding true in our international work. When we get to countries or regions that are really driven by oil production, they don't really care in general about the gas. And finally, because this group of super emitters is small, but it's changing to place, probably the only way to mitigate their emissions and find them is to establish a frequent or even continuous monitoring program that is able to detect when these things are happening. So moving away from super emitters, just to wrap up our US work and where it's going. So there are several studies looking at this leakage rate from different production regions. And we see a wide range of those production rates. So I said before that if we were above 3%, we don't really see the climate benefits. And we see a wide range, right? So we see places like Northeast Marcellus, where the leakage rate is between 0.2 and 0.4. But we see other places like the Uinta, where the leakage rate is between 6 and 11%. So there's a wide range. It's also true, one of the things I mentioned, that it's important to have more than one flight or regional estimate. Most of them have one, so that increases the uncertainty. But what we're working right now is how can we explain this range of values? How can we come up with, let's say, national weighted average emission rate? And one of the initial hypotheses we are exploring is the last column, and it's the percent of total energy that comes from gas. That's also in line with what I just said for superemitters, in the sense that when you have a basin that it's really going after the gas, like Northeast Marcellus, you see a very low leakage rate. And then when you get to places like Weld, where a lot of it is coming from gas, is coming from oil, you start to see these other numbers. The one that we're still trying to sort out what's going on is the Uinta. It's also true that it's one that just had one flight, but we're working, and we hope that this last piece of synthesis work is going to sort of finalize EDF's U.S. oil and gas system methane work. Now, going into the global oil and gas system, this is a map of methane emissions globally. It should be taken with a grain of salt because it's completely based on what's reported to national inventories. And we already knew that for the US, that was not accurate. But it gives kind of an initial sense of, one, where do we expect emissions, and two, what's the magnitude of the problem. To summarize this, if we aggregated all the gas that it's vented to the atmosphere in the world, it would be equivalent to 3.5 trillion cubic feet of total gas produced, equivalent to throwing to the atmosphere $30 billion annually. And this is equivalent to the total gas production of Norway, which is the 7th gas producing country in the world.
Does that include flaring?
This includes, the flaring part that you don't transform to carbon dioxide. So this is just methane. But it would include flaring as a source. An interesting conversation that we've had with research groups and academic institutions, when we talk about this outside the US, everyone, there's a clear message about methane and natural gas, but there seems to be a link between methane and fracking. So when we've talked, for example, in the UK, they say, oh, well, but we don't have fracking yet, so we shouldn't be caring about this. And the important message here is that the methane issue is related to the oil and gas system as a whole, regardless the type of production or processes that are being used. So even in countries that have banned hydraulic fracturing, if they have an aging oil and gas system, chances are that methane emissions are going to be high. We've divided our project into two main parts. The first of all is that we've realized that what we've seen in the US might not apply to other regions. This is a good example. So this is how a gas production site would look in the Netherlands. They call them production clusters. While in the US you see, pump jacks or wellheads spread through a wide region, and then on a separate location you would see the compressor stations and the processing plants. The Dutch have compressed everything to single location. So in the major gas field in Europe, you would just see 27 of these production clusters. the Barnett has more than 20,000 active wells. And each of these production clusters would have between 10 to 12 wellheads with the processing of the gas and the compression happening on site. So one of our working hypotheses is also that when you get to places, and this might be just because it's just one company in the entire country extracting the product, when you get to places where the system can be more integrated, you have less places where methane can get leaked, and that could reduce emissions. So the first stage of our project is what we call a taxonomy of the oil and gas system. So we're developing a catalog of location, of all the type of facilities involved in the oil and gas system, and try to come up with a classification that allow us to say, well, these three countries are similar to the US, so maybe the US and Canada are similar, and so the data that we've collected in the US can be applied there. But this other group of countries, the infrastructure looks so different that we need to go out there and study. The second stage is the actual measurements. We're going to use a similar structure like the one we use in the US. This is a project that was already announced in collaboration with UNEP. The idea is to be able to locate where we have gaps in terms of data and things that we have no clue about the emissions. One example could be just offshore activity. And we're going to go out and use a combination of methodologies and the lessons we've learned to estimate those emissions. This is just to reinforce the point about the difference in infrastructure. The top two images are in the US. Then we have one in Qatar and the one that I already showed in the Netherlands. One of the first projects we already conducted was in Europe, specifically in Netherlands. So what's interesting is that the Netherlands is the major gas producer in Europe, and the blue section of the bar would be emissions coming from gas production. So it's quite interesting that the Dutch inventory reports 0 emissions for production. So, I mean, the two possible explanations is, as we have seen in the US and other places, emissions are higher than reported and they're going to be non-zero. Or there's a particular reason related to the way they are producing the gas that causes emissions to be significantly lower than anything we've seen in the world, and then there's something to be learned about the way they operate these sites. We're still analyzing the data. We've seen that the emissions are non-zero, but they're clearly not as high as we've seen in the US. So there are some clear lessons to be learned about what they're doing. One of them is that, I mean, it's easy to control 27 production clusters rather than 20,000 wells. They're actually implementing a type of continuous monitoring on the sites that allow them to detect when something goes wrong so they can quickly fix it. Another example of the challenges we're facing internationally, Mexico and Canada follow the US announcement of a 45% reduction in oil and gas methane. And one of the discussions in Mexico was if they were going to base that 45% reduction on their national inventory that was produced in 2012, so between these two bars. Between 2010, and this is something that we saw also in the US with EPA inventories, but so if we see the last two inventories, 2010 and 2013, they adjusted some of their methods, but we see a 3.5 change. So unless we really know what is the actual baseline of emissions, this methodological change in the report would have already made the country achieve the national goal. So just a few final thoughts and interesting next steps. I've heard from different people say that if the solution to slowing climate change or man-made climate change is that world needs to get into a sort of carbon diet, as with any good diet, every now and then we need to get to the scale and know what is the actual magnitude of emissions. So there's always a need to validate and improve the inventories across the world. A way to validate is using the top-down methods, like the aircraft I described. And some countries have actually incorporated those top-down methods directly to their inventory. So this is for the inventory in the United Kingdom. The bars is the inventory, and the blue line is based on aircraft and tower measurements. So each year they are able to directly revise the inventory and see if they are off, what's going on into the numbers that go to the inventory. It is true that that happens, for example, in the US, but it's done, the top-down or validation would be done by the academic community and the inventory by EPA. So if there's a method to close the loop and make it more a continuous feedback process, it's easier to know what goes wrong. Another interesting aspect of validation is the use of satellite remote sensing. This is from a satellite that measured methane concentration for a number of years. It's not retrieving data, you cannot retrieve data anymore. It's called Schemaki. There's a number of them that allow to retrieve data. One of the interesting aspects, there was a lot of headlines in the news, was the appearance of the Four Corners hotspot in New Mexico. There are other good examples, for example, with coal mining in China, where this technology allows you to see where you have hotspots. One of the main issues here is the resolution. So usually the pixel size, I think in this case is 10 kilometers by 10 kilometers. So in a gas producing field in the US, in 10 kilometers, you can have a lot of things going on. So even if you turn that hotspot red, you might not know what's happening. New satellites, one of them is going to be launched in the summer. It's going to significantly reduce the size of that grid cell that you can get, and it's going to get data in a more continuous fashion. So the use of this new, exciting satellite remote capabilities can allow us to do a more continuous check in the inventories. The other aspect that it's also relevant is that there are certain places where we found extremely difficult to get emissions reported, certain countries. So this provides sort of an independent, transparent way in which you sort of apply the same methodology across the globe. Another example, just to locate, for example, oil and gas infrastructure when it's harder to use, where you can't really rely on what's reported by the governments, is to use a concert of this satellite remote sensing data sets to know where infrastructure appears. So this is the Persian Gulf, Middle East. This is data retrieved from two satellites. The one with the red spots is SO2 and NO2 concentrations from OMI. And the one in the center is a nighttime lights data set, which filtered specifically for signals that look like flaring. So when you're able to overlay all of these signals, even if they are not methane, they can give a first glance at where the infrastructure appears. Another project that we conducted in the US and we're also taking internationally, we partnered with Google, and we used Google Street View cars equipped with a methane sensor to drive around cities and get a sense of leaks in different cities. We have more than a dozen of cities. Some of the interesting conclusions here, for example, we compared Boston to Indianapolis because Boston has an older pipeline system. We were able to observe a higher number of leaks. This has also received a lot of interest from the companies in charge of the pipeline system in the cities because it provides a good way to know which are the most dangerous leaks and the first ones that they need to fix. And finally, I'll finish with the idea of mitigation and the fact that we know what to do about this. We've conducted cost-effectiveness analysis listing the wide array of technologies that we have nowadays to control methane emissions. And it's important to underscore that when the methane is not leaked to the atmosphere, it's a product that you can sell if you're able to send it to the pipeline. So this is why a lot of the solutions actually transform into profits for the operators. We've done this type of analysis for the US, Canada, and Mexico, and in all three countries, you would be able to achieve almost 50% reduction in the emissions, and the increase in the cost of natural gas would be less than a penny per 1,000 cubic feet of gas. So this really reinforces that the idea of looking at oil and gas system globally and methane emissions is that we have nowadays a good solution to speed the rate of climate impacts in the world. And with that, I'll take questions.
So, question and comment. So for everyone's benefit, I'm Dave Allen. I was Daniel's thesis advisor. One of the big holes in the natural gas supply chain in terms of measurements is liquefied natural gas, compression, loading, shipping, unloading, and getting back into the pipeline system. Any plans for any measurements
Yes.
on those?
So we know for sure, even before finalizing this taxonomy of what we know and we don't know, we know two unknowns for sure, and we're going to do measurements on those. One is LNG system, and the other one is...
And where are you going to do the LNG?
We're still
negotiating?
Yes, still negotiating.
I'll ask you later.
And the second one is offshore, emissions from offshore.
Okay, so then comment. I, with you, wonder a lot about the variability from field to field. And one of the ideas that has struck me is that I certainly agree with your hypothesis that looking at the percent of energy that's due to the gas is a good thing. But it wouldn't explain a phenomenon like the San Juan, where it's all gas, but you get a lot of emissions because there's a lot of water. So it's not so I would propose putting in perhaps a secondary criterion that would be total liquids production, and part of what causes the emissions to be different, the problem of the gas-liquid separation, regardless of whether it's a hydrocarbon liquid or water. So just a thought.
No, and so just to close that idea, so I talked about the taxonomy outside of the US, but actually, so that table I showed, we're trying to build a taxonomy of regions in the US, listing a few characteristics like the one you described in the San Juan that can help us bring to light those parameters that are driving the different leakage rates.
So I had a quick question. You're mentioning the compressor stations in your analysis, and you said there was actually 10 times more emissions than what the equipment initially said when you were doing your analysis. What was the reason for that? Was
So
just the equipment was too old, wasn't good at
10
registering?
times more facilities. So when we mapped the ones that appeared in official reports, we got 25. And when we started looking in Google Earth for the actual ones, we saw, and we pulled other records and permits, we figured out there was 10 times more. It's like if you don't have the accurate number of wells, you're never going to get the inventory right.
Yeah, I was hoping you could enlighten us for, if you zero down on the number of wells, like for example in Texas, and the total carbon footprint generated by the complete footprint of each well. Because I've heard that each well is, 12 to 18 months of production, and then you'll have 1,000 to 1,500 18-wheeler trips to supply that well with sand and water and chemicals. And so if you look at a total analysis and then all the diesel fuel, all the energy that it takes to get this energy, How, do you look at things like that?
So, and we need to think so of all those processes that go even before the well is actually on production, what's contributing to methane emissions by itself, right? So all of those things are going to have an environmental footprint, but if we look at methane, and we've looked at the different processes that have done this, for the Barnett, and I know that's what you would be after, we would get to this 1.5% leakage rate. But that includes everything that happens from the moment the well is kind of starting production, which is a completion, to the moment the gas gets to the city and it's distributed in the cities. So it's trying to account for emissions across the supply chain. Does that get to your question?
So no, it doesn't have the embedded CO2 from...
Yeah, so this is just,
So it's really partial. I mean, is it, am I correct?
So,
in saying
well-
1,500 18-wheeler trips per well? Is that wrong? Or?
So there's two parts to that. So the 1.5% is just accounting for methane emissions. However, this technology warming potential framework that we use to analyze if you need to be at 1.5 or 3%, includes methane emissions from CO2. So those would take into account the CO2 emissions also across the supply chain. We could get into discussion about how good are the estimates about those emissions, but in order to get to, you need to be below 3% for that technology switch between coal to natural gas to make sense. It's including methane plus CO2.
Yes, over the last decade, there's been a massive shift in Mexico from generating electricity with fuel oil to burning natural gas, most of which is imported from the U.S. And from what you know, do you think that's helping the environment or neutral or hurting it?
Well, it depends if we try to answer the question as environment as a whole or particularly for, let's say, climate perspectives. And because, I mean, using whatever fuel or energy system we decide to use, it's going to have its own implications. Like what I was saying with the diesel trucks to natural gas, you can decide not to do that from a climate perspective because it's very hard to be below the 1%, but you might decide to do that just because of the public health air quality benefits of reducing other pollutants. So for this particular question, it's also important to consider, even if we were just talking about climate benefits, that the efficiency of the plants in Mexico, it's expected to be different than in the US. And one of the things we're proposing for Mexico, and it's one of the countries we've included, that we need to do a similar analysis to the one we did in the US, but in Mexico, to be able to answer if those types of technologies switches make sense from a climate perspective.
So has there been any correlation between, say, the financial health or size of the companies in the U.S. who have these, who are the operators? I realize in other countries it may be a national oil company or gas company, but in the U.S., for example, could it be a large company that may have more financial resources, or looking at their financial health to see if they're, you know, ones that are more financially healthy, they're the ones that have the resources to maintain their wells more? It seemed logical that you could have some under duress and they can't maintain it. Any correlation there?
Yeah, so we're still looking into that, both the U.S. and globally, but there seems to be a relationship in which the bigger players have this availability of resources and incentives to reduce emissions. So when we were flying with a helicopter, there seemed to be a difference in which, I guess, the companies we all know had less of a contribution of supermeters, and they are the ones that probably have the most up-to-date technology and infrastructure and more resources to deal, for example, with a malfunction that would cause one of the supermeters. So yes, you're in the right direction based on what we've seen.
So one of the examples was of the infrared picture of the tank that was super emitting.
Yes.
So if that's a condensate tank, did you do any like diagnosis of what would have been malfunctioning upstream of the tank? And if so, what's the proposed solution?
Yeah, so we've been studying that for quite a while. There's a group of things that could cause that type of emissions. And as you say, it might be related to something upstream of the tank, like an issue, for example, with the separator. We've seen cases where, well, so a solution would be to install some sort of vapor recovery unit or to flare the emissions. We've seen cases in where there's actually a vapor recovery unit, but it's not operating as expected, so that's causing also the venting. There were other interesting examples in that data set of footage in which the emissions were coming out of a tank because the hatch was left open. So that's one of the other examples of a very simple fix to super emitters.
I'm wondering if on the economics for like the vapor recovery units, you said that they're economically feasible. Did you account the frequency of those super emitters? Because if only one in like 20 tanks is emitting that much methane, then that affects like the cost, you know, the payout for that piece of equipment.
Yeah, so we took kind of a first pass at that during the, so this cost analysis study would take vapor recovery units and tanks as one of the solutions, in assuming that the emissions comes from the measurements we've taken, so that frequency of super emitters. And it still shows to be cost effective to do it.
So on this slide, especially for the ones on the left that have a negative cost of conserved methane, if you will, what would be the payback period for some of those technologies? And that's part A. Would it be within the production time of the well?
Yes.
Okay.
Yeah.
And so part B, what I'm wondering is, because earlier you were suggesting that part of the problem with some of the emissions, especially that are very high, is that they are associated gas, and the primary product is petroleum. So the value of the gas is very low. For something like that where you have stranded gas, how would you take some of these kinds of issues and say, well, now we want to mitigate and we think these are the cheapest options, but you're not going to pay it back because gas can't get to market?
Yeah, so a good example for that, and it's when we, and I don't have it here, but when you see this cost curve for Mexico, so Mexico has significant oil-producing regions with significant associated gas. So what we propose there for this analysis is, okay, you're not going to be able to send the gas to the system to sell it. At the very least, you should flare it. And so the one we propose for Mexico is flaring. And actually, when you do flaring of that, all of that associated gas, you end up with this still less than a penny per Mexican 1,000 cubic feet of gas.
So I've been hearing a lot recently in the news about emissions from university-owned lands. Do you have any thoughts about that?
So I would say 3 thoughts. One, without having measured university lands, I wouldn't expect initially anything differently in terms of their emissions. What I mean by that is they're probably underestimated. You probably have super emitters happening, and you definitely have cost-effective solutions to those problems. And I would say that the fact that they're university lands, on one, should perhaps provide an incentive to get the reporting right, and to have the opportunity to send a strong signal, especially because they are cost-effective solutions, to say, we can take the first step, sort this out, and show how easy, in a way, it is to deal with this problem.
So are there ways to radically reduce the cost of monitoring without the airplanes? I mean, are there drones that can be automated and flown over these things so it can get down to a low enough cost where NGOs or other organizations, if governmental entities choose not to police this, that they can look for these super emitters and then perform a function of helping to isolate and identify them?
Yeah, so there are a few projects actually using drones to do that type of monitoring. There's one particular, for example, there's one company, startup company in California, they're called Kairos. What they designed is a methane sensor. They mount that to a Cessna. They can basically fly over one of the U.S. gas fields in a day or a few days, and after the end of that coverage, they tell you, oh, those 3 sites are super emitters. So the idea is that they're selling this technology to the operators as a way, instead of sending your own inspectors to look like hundreds of sites, you can use this technology. We have one initiative. We have what was called the Methane Detector Challenge. We partnered with industry and startup companies. The idea was to develop a very low-cost sensor with the idea, if it's significantly low cost, you can install one of these little sensors at every single site, and those would ring an alarm if you see a super emitter. And they just installed the first one in I think it's a site in the Eagle Ford, and they're testing if it's actually good at detecting high emitters.
Sounds like a good capstone project for the aerospace engineering department. Figure out a way to put these things on drones and go make some money at it. We got time for maybe one more question. Is there one more?
I can ask one.
You fully addressed it. Thank you very much. Round of applause.
It's okay.
Oh, I'm sorry.
Okay, I had a question. I'm sorry. But talking about news, so let's say we invite you to speak for the symposium 6 months down the line. Do you believe you're going to give the similar presentation, given the present administration and the question about EPA's data? Because I'm assuming you have gathered a lot of data from EPA's, some kind of data. So are you expecting to give the similar presentation, or the line in the climate benefits is just going to go out of the screen?
Yeah, that's an interesting question. I mean, so on one side, the EPA has been extremely, until a few months ago, and this is just because I haven't engaged a lot in the last months, but they've been extremely active in iterating on their inventory and getting it better and better and really understanding what's going into the emissions. We're hopeful that the technical people in the agency are able to keep that role. And I started with that because if not, it would just seem that I'm just trying to go another direction with the question. But if I was invited to give this presentation 6 months from now, I would hope that we have a better glance at what's happening globally. And we actually think that showing the magnitude of the problem globally and getting other countries in line with doing this 45% reduction, we can get. So initially, perhaps we thought that U.S. was going to be the spearhead in this type of climate work, and we hope it's still there, but we think that with the arguments of the magnitude of the issue and the cost effectiveness, we can make other countries get on board with this strategy.
Yeah. Thank you, Daniel.
Good question.
No.
I think it was a rhetorical question.
Yeah.
Thank you.
Question for you. That slide that showed the tanks.